Hello, my name is Valeria Olvera-Cázares and I will present my poster, Synthesis and Characterization of Lignosulfonate-GRAFT, NETPOLY, METHACRYLAMIDE-CO acrylic acid by conventional free radical copolymerization using microwave activation for lead removal. For the 33rd International Materials Research Congress, 2025. The co-authors are María Fernanda Munguía-Quintero, Alberto Rosas-Aburto, and Eduardo Vivaldo-Lima. This research took place in Universidad Nacional Autónoma de México, Facultad de Química, México. Ciudad de México, 04510, Mexico. Adsorption is a remarkable application of polymeric materials, including hydrogels, which are hydrophilic polymer networks composed of several interlinks, crystalline regions or crosslinks that contain functional groups such as carboxylic acid, sulfonic acids, hydroxyls, and amides. The absorption's performance depends on the monomers utilized in the synthesis. In this contribution, the synthesis and characterization of lignosulfonate-GRAFT NETPOLY METHACRYLAMIDE-CO acrylic acid hydrogel were carried out by conventional free radical copolymerization using microwave activation. The effects of the concentration of lignosulfonate obtained through a process developed within our group, known as the gas phase acid pretreatment GPAP process, methacrylamide and acrylic acid during the synthesis were evaluated on lead absorption performance. The objective was to synthesize and characterize lignosulfonate-GRAFT NETPOLY METHACRYLAMIDE-CO acrylic acid hydrogel by conventional free radical copolymerization using microwave activation and evaluate the effect of lignosulfonate concentrations on the performance of lead removal. For the synthesis, sodium lignosulfonate LSNA and methylene bisacrylamide NMBA and ammonium persulfate APS were mixed with distillate water. Subsequently, methacrylamide MAM and acrylic acid AA that was neutralized with potassium hydroxide, KOH 0.1 molar, were added. The solution was placed in a microwave oven for 5 minutes at 100 watts, washed with ethanol and distillate water, and finally left to dry to recover the hydrogel. We have this table in which we can identify the amount of sodium lignosulfonate in the HM6-2, HM7, and HM9 hydrogels. We have the biggest amount of LSNA for the HM2 hydrogel, then the medium amount for HM9, and lastly, we have a zero amount for the HM7, which was our reference hydrogel. Next, we have the FTIR plots, which illustrate the spectra of the three hydrogels and allow us to identify certain peaks that characterize their functional groups. On the second and third plot, we have assumed for a better visualization. The first peak corresponds to the CH alkene bonds. The second peak represents the aldehyde bonds. Third, fourth, and fifth peaks represent the CO amide bonds. Sixth peak represents the sulfones bonds, and lastly, the seventh peak represents the CN amine bonds. For the fourth plot, it shows the removal percentage versus time. The tendency of the hydrogel's removal is to increase as the time goes on. For the fifth plot, it shows the HM2 removal versus time for different initial concentrations. We can appreciate that the HM2 performance is better in 25 and 68 ppm initial concentrations. And last but not least, it shows the HM9 removal versus time for different initial concentrations. We can appreciate that HM9 performance is better with the 25, 50, and 100 ppm initial concentrations. In conclusion, the addition of sodium lignosulfonate LSNA in the synthesis of the hydrogels showed a significant improvement in the absorption capacity of Pb2 ions. The reference hydrogel HM7, synthesized without LSNA, achieved 58% removal of Pb2, with an absorption capacity of 58.24 milligrams per gram. This effect has been reported by other authors, who have observed that high concentration of lignosulfonate can affect the absorption performance. I would like to thank the DGAPA UNAM Project PAPIT for providing me a scholarship during my research. Thanks for watching.